Hi, I've now brought you inside the Prisma MRI scanner room. And as you can see, behind me there's, well, me again, and I'm putting a participant inside the scanner ready to do our experiment. One of the most important things is to give the participant earplugs because the radio frequency pulses emitted by the scanner are very loud. And obviously this is a big problem if the participant is trying to sleep. Also, you need to make sure that both of you are free of any metallic objects because the scanner is a big magnet, remember? So metal in the scanner room is a big no-no. So our participant is inside the scanner. We've made sure he's feeling okay, he's relaxed, he's comfortable. We've read him his bedtime story. Capybara is a capybara. And he's fallen straight to sleep. Now we need to wait maybe 20-30 minutes for him to go through stage 1 and stage 2 of sleep before he enters the strange and mysterious realm of slow wave sleep. In this stage, the neurons in your brain synchronize, all firing together on and off, on and off. And if you look at the electrical activity of this neuronal firing, it forms a sort of wave, a slow wave. In many ways, this is the opposite of what your brain is doing while you're awake, where things are much more chaotic with neurons in different regions, all firing at different times. Slow wave sleep is where our old friend the hippocampus comes back into play. So if you remember, that's the part of the brain that's responsible for forming new memories. During slow wave sleep, the hippocampus gets busy doing something we call memory reactivation. Think of it like a highlight reel of your day, where specific memories are reinstated or replayed, and this helps to strengthen them and store them in your long-term memory.
Look, horse.
But the hippocampus isn't acting alone. It's actually communicating with lots of different parts of the cortex.
Hey, frontal lobe.
All right.
Parietal lobe.
Alright, love.
Occipital lobe.
Guten Tag. You can think of slow wave sleep as a time when your brain files away the most important things that you learned and encountered during the day. This ensures that your brain is ready to learn new information the next day.
Look, horse.
What's really cool and quite sci-fi-y is that we can actually trigger this process in our sleeping participant by presenting smells and sounds. In one famous study, researchers presented the smell of roses while their participant learned a memory game. Later, when the participant was asleep inside the scanner, the researchers pumped the smell of roses back into their nose holes, and they saw activity in the hippocampus.
I remember.
It was as if the smell was helping to reactivate the memory game that they played before they slept. And when the participant woke up, their memory had improved. This is another indication that the smell was able to reactivate the memory game and strengthen it in the participant's long-term memory. This is a very popular area of neuroscience at the moment because there's still so much we don't know. Like, how does the brain know which memories to replay and then remember and which memories to forget? I just want to finish by saying that slow wave sleep is not all about memory. So there's so many things it's involved in. There's the glymphatic system. So there's this process of your brain essentially getting flushed overnight with cerebrospinal fluid. And that might be important for removing neurotoxins that are involved in Alzheimer's, for example. Slow wave sleep is also important for thermoregulation and supporting the immune system. There's the release of growth hormone, which is important for everything, like loads of things, but muscle development is one example. Synaptic downscaling, I mean, that's a biggie. I should probably do another video on that. Also, a lot of sleep disorders happen during slow wave sleep, like sleepwalking and sleep talking. Sleep tennis, is that a thing?